Good afternoon to everybody. Thank you for taking the time to listen to me. Let me briefly tell you about what I'm going to be discussing. Okay, I'm just going to give you a little introduction to myself and to Olympus, and then I'm going to talk a little bit about circuit breaker theory. I'm not really trying to make you an expert here. I just want to bring out the important points that will inform you as to why the circuit breaker monitoring system that I'm discussing is the way it is. And if you were looking for a sort of a tutorial on general circuit breaker monitoring, you might be a little bit disappointed, because I'm really talking about something very, very specific to shunt reactors, which are quite a difficult application for circuit breakers. I'll give you show you some of the typical signals we've got, and I'm going to show you a lot of the defects that were discovered by this this approach. This has all been done in cooperation with National Grid, and it's really been very, very successful. And I think you'll find when I show you some of the results that it's produced advance warning of issues that otherwise would have pretty much gone unnoticed. So a little bit. Well, let me tell you a little bit about myself. I served my time with a company in the Midlands called GUC Measurements, and those of a certain age will know that they used to make protective relays, eventually taken over by Alstom in the 80s. And I, following the change to Alstom, I moved and I went into academia, and I spent the next 20 years teaching electrical power systems in various universities, and I wound up at the University of Strathclyde as Professor of High Voltage Engineering in 2005. And during my time in academia, I'd spent a lot of time researching the radio frequency emissions from high voltage plant. And this ultimately resulted in the development of a radiometric partial discharge monitoring system, which the University of Strathclyde spun out in 2007 to form Olympus. And I left the university a little bit later, and I've been the full-time director of Olympus ever since then. We started out making and providing services for PD measurement, but more recently we've moved into more generally condition monitoring. So we now install DGAs and SF6 gas density monitoring, and sort of recently, although not particularly recently, we've started providing circuit breaker monitoring. So I'm going to, during this presentation, explain to you how the monitoring system works, and as I said, I'm going to give you some of the results. And this was from a 2-year trial that we did in cooperation with National Grid. So a little bit about circuit breaker theory. So circuit breakers essentially contain contacts which can produce an arc. So I've shown this. I'm not trying to show you a very accurate model of what's inside a circuit breaker. I'm just trying to elucidate the essential details so that you'll understand why we're monitoring the way that we are. So you can imagine the top slide here, the top graphic is showing you two contacts pressed together that allow the passage of current. And if you were to separate those contacts, then you would end up with an arc between them. I've shown here the contacts moving, both of them moving. Usually in a circuit breaker, one of them is fixed, and only one of them moves, but the effect is the same. And that's a very good state of play for a circuit breaker, because you know exactly where the arc is. And the reason you know where the arc is that when you move these contacts apart, you don't get an arc in it at the outset. When you start to move them apart, what happens is you melt the contact material and you draw out a very thin thread of molten material, which then develops into an arc. So you can actually guarantee that this arc is going to be across these contacts. And that might sound a very strange thing to say, but you will see in circuit breakers, sometimes you get arcs where you don't really want them. Now, the other important aspect when you are dealing with arcs is you have to control it. And so in all of the circuit breakers that I've been dealing with, particularly in this trial, we've used, or the circuit breaker uses sulfur hexafluoride gas to cool the arc. So I'm trying to show this by these yellow arrows which cool the arc and make the arc smaller. If you were dealing with the earlier generation of circuit breakers, you would air blast circuit breakers, the gas would be compressed air, but it's the same principle. You might think that if you were to continue moving the contacts apart and continually cooling it down with a supersonic flow of sulfur hexafluoride gas, eventually the arc would go out. And the true reality is it probably won't, because once you've started an arc, it's very difficult to get rid of it. But the reality is in a 50 Hertz system that you don't have to wait very long until there's a zero crossing. So I can just demonstrate the ideal state of affairs to get rid of an arc. So you can see here on the right hand side, I'm showing you the current through the arc. This is represented by the white arrows. The yellow arrows are just to remind you that SF6 gas is being used to cool the arc down. So maybe at T1, time T1, this is just a few milliseconds after the penultimate zero crossing, you begin to separate the contacts, and then at T2 we've got an arc going. As I said, you've pulled out this little thread, it's then developed into an arc. By the time it gets to T3, the contacts are really quite separated, and at T4 the current goes to zero and the arc goes out, and that's the end of it. Now, in reality, actually getting rid of the arc isn't particularly difficult in a circuit breaker. What is difficult is stopping the arc from coming back, and we talk about reigniting the arc. So if you imagine these contacts are now a reasonable distance apart, there is two voltages you need to understand. One is called the dielectric withstand voltage, and that's the voltage that the circuit breaker will tolerate without the arc restriking. And then across that there's the system induced voltage, which is called the transient recovery voltage, and that's not particularly to do with the circuit breaker, that's related to the external circuit. And in the case of a shunt reactor, this gives quite a difficult situation for the circuit breaker. Let me try and explain that. So what we're looking at here is the terminal voltage, this blue trace here, the terminal voltage of the shunt reactor. So before the arc goes out, we have 50 Hertz signal, and then at this vertical dotted line, this is the point of interruption. This is voltage, so the current, the voltage is at its peak there, so the current will be at a zero crossing. So the current goes out, and we then go into this very high frequency transient, and that's caused by, as the arc goes out, you can see the current is at a maximum. So all the capacitance associated with that shunt reactor, the capacitance in the windings or the bushings or the bus bars connecting it to the circuit breaker will all be charged up to system voltage, and probably a little bit higher because you've got the arc voltage to add on to that as well. And as soon as the arc goes out, that voltage then starts to resonate with the inductance in the reactor, and it resonates at a frequency of about 1500 Hertz, maybe 1500 to 2000 Hertz. It just varies on the different sort of applications. And the reason that that's a problem is that if you look at the point of interruption, if we go about half a millisecond beyond it, then the system voltage, the bus bar voltage, is going to be pretty much the same. It's just going to be the peak value there. But if you have a look at the reactor terminal, at about half a millisecond later, it's gone almost to the negative value. So we're now seeing roughly 2 per unit across this break. So, and that's why it is so difficult to interrupt shunt reactors, because as soon as you get rid of the current, you get a very large voltage very quickly across the contacts. There's also an effect there called current chopping, and I'm just going to miss that out. If you want me to explain that, please write a little note and I'll say a few words about it. Now, what I want to talk about just for a moment is how you cope with that. How do you ensure that the breaker doesn't reignite the arc when you end up in this oscillatory period? And one of the things, and this is a very, very common at all 400 kV breakers is that you would have actually two sets of contacts or two sets of interrupters in series. So you can see there's one set here and there's another set there. So what you're really doing is you're divvying out the transient recovery voltage across the two gaps, which allows the breaker a greater chance of breaking the arc and ensuring that it doesn't come back. The problem with that approach per se is that this middle point, the point here, is in fact floating when the arc goes out, and that can sometimes lead to unequal voltage distributions across the contact gap. So it's more common to see a capacitor put across the contacts, which is called the grading capacitor, and you can just see that in these. I've just highlighted that in orange. You can just see it's bolted on parallel to the interrupter, and what that does is it more or less guarantees that the transient recovery voltage is in fact equal across the two gaps, so that they both sort of work equally towards stopping the arc reappearing. And the next thing you can do to stop the arc reappearing is to use what's called control switching, and you've already seen control switching. This was what I showed you earlier. So this is where you arrange for the contacts to part at a couple of milliseconds or so after the penultimate zero crossing, which means that for the majority of the current, the arc is burning, and then it gets to the T4 point where the arc goes out, and this is where the contacts are now far apart, and that's the ideal state to be in, because the problem is that if you don't control that operation, the point at which the contacts separate is essentially random. Let me try and show you an example of that. So this is one random point where you might separate the contacts, which is at this point here, T1. So it's sort of just a little bit after the negative peak. So the contacts separate. So by the time we've got to T2, we've got a nice arc burning there. But by the time we get to T3, and the contacts aren't sort of fully separated here, but they're a reasonable distance apart, the arc now goes out. And then a little while later at T4, the transient recovery voltage caused by the reactor transient causes the arc to restrike or reignite, to use the proper terminology. And you might say, okay, well, all right, so the arc reignites, so what? Well, the answer is that when the arc reignites, you don't know exactly where that arc's going to be. And you might think, well, surely that can't be the case, but these contacts are pretty close together, and it just must occur across these two contacts. Well, think about this. Think about lightning. Think about when you see lightning, particularly pictures of lightning that shows the progression of it. It's very, very random and chaotic, and it's exactly the same in a circuit breaker. That when the arc ignites, it doesn't reignite along all of the path simultaneously. It reignites in little bursts until it eventually bridges the whole gap. And the danger with having a reignition in a circuit breaker where the contacts are reasonably well separated is you might get this effect. You might actually get the arc deciding not to go through the bit that you expect it to. It might go on the outside, in which case it's no longer going through the gas flow and it's no longer being controlled. And if you have that situation, then you are in a very bad situation from an interrupting the shunt reactor point of view. And I will show you the effect of that in some of the results that I've got when we get on to the defects section. So just a little bit of a summary there. I'm sure you all know this, but I'll repeat it anyway. So in a circuit breaker, we interrupt the current by using a natural zero crossing. The interrupter creates an arc which allows you the contacts to get far apart before the arc goes out due to the zero crossing, which then provides this dielectric withstand voltage. You control the arc by the gas flow and the contract separation. Interrupting the arc generally is easy, but preventing it reigniting isn't. That's the difficult thing. reignitions ideally should not occur. They are a problem in circuit breakers, especially in shunt reactors. We use grading capacitors because they equalise the system voltage across the two contacts when the arc's gone out. And finally, control switching relays are more or less universally used now. I don't think if you were putting in a transmission voltage shunt reactor today, you would use a breaker without a control switching relay. They're almost synonymous to good practice. Okay, so that's our brief run through of circuit breaker theory. Let me tell you a little bit about this circuit breaker monitoring system. The circuit breaker monitoring system I'm going to describe has been developed over about the past 20 years, and don't by that take it to mean that Olympus has diligently worked away at being able to produce a very good system. It has started out as an idea which every few years, due to a fortuitous conversation with somebody from a utility, has then taken a leap forward and a little trial and a bit more development of hardware, and it has taken us 20 years to get to the point where we are today, which is something that's doing something quite useful. The circuit breaker monitoring system is based upon service conditions. It's not an online test. If the circuit breaker is out of service, this system won't work at all. It needs the system to be in service to produce any useful results. We've trialled it entirely on 400 kV gas circuit breakers using switch shunt reactors. We've actually started doing other tests now on other applications than shunt reactors, but it's shunt reactors where it has the potentially the most benefit as we speak. The equipment was designed to be portable. It was designed to be taken around and trialled, and we found we could pretty much set this up within about 2 hours of arriving on site in an ideal world. You don't need any outage. You don't need to switch things out to do it. You can just put all the equipment onto it and bolt it on, as you'll see in some of the photographs I've got in a moment or two. Once it's been set up, you don't need to be there to see the circuit breaker operate. It just records automatically, and we can, through a 4G connection, we can get the results and log into it and see what's been recorded. So since most shunt reactors operate quite regularly, maybe every day or so, you can put this on, maybe leave it in situ for a few days or a few weeks. Just, you want to ideally record about 10 operations. That gives you a pretty good feel for the way that the circuit breaker is behaving. And we can detect defects in the mechanism and the drive system, the damping, the interrupters, the control switching relay, and the grading capacitors. And you now see why I did all that CB theory stuff, because if we hadn't done that, you might not have entirely got the idea of what these points are. This gives you an overview of the way the monitoring system operates. I'm showing this on an air-insulated circuit breaker, but it has been equally applied to GIS. It's just a slightly different application. So we have a monitoring box with all the recording hardware in it. We then record the trip and close signals. Normally you get that from a little monitoring kiosk which is close to the breaker. In a circuit breaker that has a control switching relay, there will be 3 trip signals. We record that by putting a little clamp over the wiring. There's nothing invasive in any of this. There's no more invasive than opening the cabinet door anyway. We measure the close as well. In all the breakers I've looked at, the close has all been common, so there's only one of those. We measure vibration. The vibration gives you an idea of what the mech is doing, what the mechanism and the drivetrain is doing, and there's one fitted onto every phase of the circuit breaker. And then finally we measure both the electric field and the radio frequency emissions. These are normally done from the same sensor, and again they are bolted onto the side of the circuit breaker. In a GIS you would use the internal PD sensor to do this. So I think I've probably talked about this. The vibration tells you about the mech. The radio frequency emissions give you an idea of what's going on with the interrupters and grading capacitors. The 50 Hertz electric field basically acts as a voltage transformer for the reactor terminals. No reactors have VTs assigned to them. When you open the circuit breaker, you can't see what the reactor terminal is doing. And that signal is very important because it tells you where the current goes out, where the arc stops, and it also tells you about reignitions. We need the trip and the close for mechanism timing, and that's common with all circuit breaker monitoring systems. You might want to have the line current measured. We are increasingly doing this, but on a shunt reactor you don't need it at all. You can see as much as you need to from the electric field signal. This is so there are two photographs just showing how the sensors are attached. So this is the vibration sensor. This is we normally try to attach. This is the bottom of the mechanism in this particular circuit breaker. So we normally try to put it close to the mechanism. In reality, it really doesn't make too much difference in where you put it. When a breaker operates, the whole frame shakes quite a lot, so you could put it pretty much everywhere. What you do have to do is put it on the same position on all the phases, though. Similarly, a similar comment with the RF and the E-field sensor. This is basically a monopole antenna, which we try to put as high up on the structure as possible so that it gives the best measurement of the E field. It doesn't really make much difference for the RF, but the E field, it benefits from being higher up on the structure, and not so high up that you need to work from height or switch anything off. Just as high as you can get it without any safety from the system implications. And this shows a typical example. Here's the box. This is very much a beta version, so it's all lots of wires hanging out of it, but it's all designed. It can be out there for weeks. Close the door, it's completely weather tight and sits there, monitor automatically, and then all the cabling takes all these sensors in and then fitted into the connections on the bottom of the cabinet. So a little overview, probably just to repeat what I said earlier, but just put a little more substance to it. So this is an overview of the measurements. So here we have the reactor voltage. You've seen this before. Here's the 50 Hertz, eventually culminating in the device interrupting, and then we go into this high frequency transient, the reactor transient. I'm showing here the line current, whether we measure it or not, but here's the current goes out at the point of interruption. And then here is the trip signals. The trip signals occur in there at about 12 milliseconds or so. And so we're measuring vibration. We measure the vibration all the way through, but from the trip signal to the point of current interruption, we're looking to see the progress of the mechanism. And then from the trip signal onwards, we would look to see whether there's any issues with the damping. Probably actually damping does maybe slightly more relevant a little bit earlier on. In the part where the arc is burning, so when the contact's open, which as we've said, ideally occurs just a little bit after the zero crossing, as the time the arc is burning, the RF emissions are going to tell us about what's happening in the interrupter, so it gives us an idea of how well that's performing. And once the arc has gone out, once you're into this period, then RF emissions tell us about the two things. It tells us about the grading capacitor, whether there's a problem with those, and secondly, whether there's a PD issue. I'm going to show you some typical signals now, just in isolation, just to explain what it is that you would see when you take a measurement from a breaker opening a shunt reactor. It could be opening or closing. Its opening is by far the sort of hardest thing to do. So these show typical signals from the RF side of the device, and there are essentially four separate things that we see. We can see arc instability emissions, and you have a look at that signal, and that is in the low tens of megahertz spectrum. It's not a high frequency signal at all. It's also not a particularly nuanced signal. It's really very easy to measure that. It's quite large, but it's only there during the arc, so it's a bit of a sort of a blink and you'll miss it thing. And the reason you get this is that when you draw the arc and you blast it with gas to try and cool it down, the arc doesn't stay still. It moves around, it curls on itself, and then it connects with itself. It gets shorter, it gets longer, it changes its attachment points. And at all of these positions, it produces this RF emission. And as a general rule, those RF emissions should be the same on all three phases. It might not be over one operation, but if you looked over 10 and you average the number of RF emissions, it might be, you know, between, I don't know, 3 and 12. It's that sort of level. You know, it depends upon the manufacturer, design of the interrupter. The presence of arc instability emissions isn't really good or bad. They're just there. They're just the way that the thing works. But if you were to see a big difference between one phase and the other two, that tells you there's something gone wrong. So if there's a lack of emissions, it usually means the arc is not where you expect it to be. And if there's a large number of emissions, it could be that there's been some damage done inside the interrupter. The next signal, which is the second one down here, which looks very, very similar, and it's also in the low tens of megahertz, is what happens when the grading capacitor fails. And I'll have a lot to say about that in just a few moments' time. But those two are very similar, and the only way you can really tell them apart is to know whether the arc is burning. So that's why the E field is so important, because you know exactly the point where the arc goes out. The third signal here is a reignition transient, radio frequency transient. Again, that's quite low frequency, but it is extremely high amplitude. Even a tiny reignition will cause our system to clip. So they're very, very easily understood. They shouldn't be. In an ideal world, you should never see a reignition transient on a circuit breaker. But if you do get them, then that's one of the ways you'll know that you've got it. The final signal there, and you can say this is much higher frequency, this is in the hundreds of megahertz, is a partial discharge from other parts of the breaker. And what we tend to see is that when the breaker operates, if you get damage to the interrupters, there might be little bits of the nozzle have been chipped away and they fall to the bottom of the interrupter chamber. As the breaker operates, the sort of mechanical agitation causes them to move around, and that can produce little bits of partial discharge. So it's sort of similar to you get in a GIS. Although, you know, usually large, all of these are large signals. You know, don't go thinking that they're difficult to measure. They're not. They're pretty big signals. So if you see that, then you know there's probably some issue there going on with the internally to the interrupter. And incidentally, if some of you are saying, well, surely, you know, substations are just full of noise, you must see these all the time. Well, the answer is you do, but those signals only appear when the circuit breaker operates. So it's a pretty foregone conclusion that they're due to the circuit breaker. Vibration signals. We use a piezoelectric device to measure vibration. It resonates at a few tens of kilohertz. So the raw data looks like that. So we apply a Fourier filter on it, which gets rid of it gives us the envelope. If I just move on to the next slide, I'll just show you that this is for all three phases now. So this is a typical open operation. You can see this large buildup of vibration energy, which occurs more or less on this particular circuit breaker, which didn't have a controlled switching relay. It actually occurs exactly at the same time on all three phases. But if you see, I'll have a few more words to say about vibration in a moment, but there are some very obvious defects that can be detected by looking at the vibration. in common with all circuit breaker monitoring systems, we can time the circuit breaker. So this is the trip coil current, which we measure with a current clamp. If you're thinking that's a rather strange looking signal, it's because we tend to use AC clamps because they don't require batteries and they're a lot easier if you're leaving something on site for a few weeks or so. And in reality, it's only the beginning of this signal that we're particularly interested in. I know there's a lot of work being done on sort of characterising this signal, but that isn't particularly what we're interested in. All we need to know is when has the mechanism been instructed to start moving, and that's at this dotted line, pink dotted line here. I've shown this with line current, and if I'd had time, I'd have changed it to a slide that showed you with the terminal voltage going from the 50 Hertz to the reactor transient, because it occurs at exactly the same point, but you can measure the time from the circuit breaker being told to operate and the current going out, and you can see that allows you to do it. And that's, as I say, that's an in-service measurement. That's not an offline test. That's actually being measured as the device is operating. Okay, let's talk. This is the interesting bit now. So let's talk about some of the defects. I'm going to start with a defect that probably, had it not happened, I don't think I would be here discussing this with you, because this was something that we detected on a circuit breaker, which ended up with quite a big implication. So let me just tell you what you're looking at there. Here's the result. This is almost 10 years ago, looking at November 2015. So this was back before we had quite the equipment that I'm using today. But anyway, we were able to measure the trip coil. So you can see the trip commands occurred at 0 there. Again, we had this idea of using E-field sensors, which gives us the point at which the current interrupts, going from the 50 Hertz to the transient there. So this is the terminal voltage of the reactor. And back in 2015, we were actually measuring the radio frequency emissions from both breaks of the interrupter, both the left and the right hand interrupter. I'm actually referred to these as interrupter 1 and interrupter 2 in this particular slide. So you can see here the arc has gone out at about 27 milliseconds after the trip coil. So at 27 milliseconds, you can see interrupter 2 had a couple of impulse. This is just showing you the peak value of the impulse. It doesn't show you the waveform. So it shows a couple of impulses there which have come. This is arc instability. There's slightly more on interrupter 1. There's a little train of them there. But you can see that after the arc's gone out, on interrupter 1, we get this large emissions of impulses which were coming from the interrupter 1, whichever one that was. And that was actually due, well, we didn't realise it initially, that was due to the grading capacitor. So we reported this, and the utility were very kind enough to actually investigate this for us. So what they did is they took off I think this is on the red phase, so they took off all the red phase capacitors, and they also took off the yellow phase because that was the phase next to it in case we hadn't quite got it right. And they took it to an HV laboratory and they tested them all. So they tested for the inception of PD, which you need an HV lab to do this. It's very difficult to do it anywhere else. And you can see that this red phase interrupter 1, the PD came at about 9 kV, whereas all the others, it was, way above, not less than 37 kV, so very, very different. There's also what's called the dissipation factor, and the dissipation factor tells you where the current that flows into the grading capacitor, it should really be exactly at 90 degrees to the voltage. It tells you whether there's any slight phase angle in that, because any slight phase angle means that the current that's going into it is actually producing some heat. And you can see again that this red phase interrupter had a very high dissipation factor. So pretty much a smoking gun there, very conclusive proof that that there was an issue there. But in fact, we've got even better results, because they actually then went ahead and took it apart. So let me just show you here. So this is just another picture of a circuit breaker. So here's the interrupter and here is the grading capacitor. And if you were to take one of those apart and actually take the porcelain off it, you'd end up with something that looks like this photograph on the right hand side. Now, to be perfectly clear with you, that is not the grading capacitor that came off this circuit breaker. That is actually one out of a GIS. And in GIS grading capacitors, they normally use SF6 gas to insulate it, whereas in an AIS there's usually oil. So when you take these apart, you have to let all the oil out. But the grading capacitor, if you've never seen one looks like this, it is actually about 200 individual capacitors all connected in series, and each individual capacitor looks a little bit like, for lack of a better description, a Dairy cheese slice. It's just a maybe a 50mm square piece of plastic, and what it is 2 bits of foil, aluminium foil, with a mylar plastic sheet separating them, top, bottom and in the middle, which is then folded over itself time and time again until it looks like a Dairy slice. And so what they were able to do with this particular one, the one that had failed, was that they took it apart, and the first thing that they noticed when they took it apart is that the oil that came out of the grading capacitor was black. It wasn't, mineral oil coloured. It was very, very badly disadvantaged. And when they unfolded quite a lot of these individual units on it, they discovered this sort of effect. It was almost as though somebody had taken a rifle and shot it through the along the length of the capacitor. It wasn't actually all the way through it, but it was through quite a large chunk of it. And this was just basically sparking every time that circuit breaker had operated. You were getting sparking inside this grading capacitor, again caused by this very high voltage due to the transient that shunt reactors produce. And that had sparked and eroded away this to the point. And this was pretty close to actually breaking down. It wouldn't have taken too many more operations, and that would have completely shorted it, and then you'd have had a very big problem on your hands. And that was one of the big firsts that we got with this technique, and probably led to further work. So let me tell you another one. Let's talk a little bit about reignitions. This was a circuit breaker, an AIS circuit breaker again, and we were asked to go along and look at it. And when we looked at it closely, you can see on the blue, this is the blue phase electric field, you can see there's a little spike there. And if I just expand that, you can see what's happened here is that this has actually gone into the reactor transient. And then for maybe 50 microseconds or so, and then suddenly the arc has reignited there. And of course, remember what I said about arcs reigniting when the contacts are apart. It's not really a very good. It's not a very good thing. And so we end up with this signal here. It also produced a very large RF signal as well, so we knew exactly what was happening. When we measured this for about 10 operations, we discovered exactly the same thing every single time the circuit breaker operated. And to cut a long story short, there was an error in the control switching relay. And instead of the control switching relay eliminating reignitions, this one was absolutely guaranteeing that you got one every time. In fact, there were two. You can see there's the blue phase there. There's also I think the yellow also produced a reignition just around about here. So it was not a great situation. However, the control switching relay was recommissioned, and we went back and we observed that there was absolutely no reignitions there at all. So again, this was a sort of a hidden effect in a bit like the grading capacity. You wouldn't have known there was an issue there. You wouldn't have known there was an issue with this circuit breaker. As far as anybody was concerned, everything was working correctly, but in fact the control switching relay had a defect on it. I've got another reignition one. This one's a little more brutal. So this is a circuit breaker. It's quite an old GIS circuit breaker in the days before control switching was a thing. And so because you're randomly switching the shunt reactor out, you will get reignitions. You can see, this is, I've chosen this because it's a particularly bad one, but you can see here there's a very large reignition there at the peak of the blue phase voltage, and there's also a very large one at the peak of the yellow phase voltage. Incidentally, I'm saying yellow phase, I use green on a white background, so it just sticks out better. So where you see green, I'm talking about the yellow phase. Now that isn't particularly, for this particular breaker, that wasn't particularly an issue because they knew that the breaker was randomly switched. They were expecting to see this. But if you just look around about 48 milliseconds or so, you can see that there is something going on there. Let me just zoom in on that on the next slide. Okay, and you can see here is the blue phase reactor transient, and look at that. You can see now there's been a reignition there. Not for very long, just maybe a few microseconds or so, and then it's gone out again. But the fact that this has happened at 48 milliseconds after the breaker was instructed to open is extremely bad news at all, and we observed this over several operations, and we recommended that in fact the breaker was taken out of service. And again, our friendly utility not only took it out of service, they took it apart and they showed us what they found. So let me show you this. This is the internal part of this GIS circuit breaker, quite an old design. This is the contacts are actually inside this glass fibre tube. One of the contacts moves on this sliding bit, and the fixed contact is removed, but it would actually be pushed in on the right hand side there. And if we just have a look at the end of this interrupter tube here, you can see these great big holes in the glass fibre, and this is caused by the arc reigniting and blasting a hole straight through the glass fibre, and instead of going through the contact, it's probably making contact with one of the metal parts inside the circuit breaker. Now, bear in mind what I said earlier, all of these breakers actually have 2 breaks per phase, so having one break doing that isn't so, it's not ideal, but you'll still be able to recover from it. If you have 2 of these doing it simultaneously, you're probably in a failure situation. So this is a very poignant example of why this monitoring was so effective. You can actually see on this one, it's actually punctured such a large hole. It's actually little bits of the glass fibre are sticking out proud from the surface. There you go. I'm running out of time, so let me just quickly finish off a couple more. This is to do with the mech. This was actually a close operation. With close, you don't get quite so much vibration signal here, so the close operation occurred at 0, and you can see here there's a little delay there, then the red mech starts to move, the blue one a little bit before it, but you can see here the yellow or the green trace. The yellow is about 15, 16, 17, 18 milliseconds after the other 2, and that is a problem because most circuit breakers have a phases not together alarm, and what that means is if it closes and it can see that in fact only 2 of the phases are connected, it automatically reopens straight away, because actually having 2 phases connected will generate a lot of negative phase sequence and 0 phase sequence currents, which are bad for the system, so they'll take it out. Now this wasn't at that point, but you can see it was going to get pretty close to it. And when this was investigated, this is a breaker with a hydraulic mech. It was discovered that hydraulic oil had actually got onto the actuator, and it was slowing the actuator as it tried to start moving the contacts. And once that was cleaned up, we tested it again, and this yellow signal then behaved similarly to the red and the blue. And finally, this is my last slide now. This is to do with damping. So just a word or two about damping. When the contacts open, they initially accelerate and they move at a constant speed. And as they get towards their maximum position, you have to slow them down, otherwise they'll sort of hit the end stops and they'll rattle the breaker apart. And you can see here that the breaker is instructed to open probably around about 18 milliseconds or so, and you get this ramp up in the vibration energy. This is the contacts accelerating, and it sort of plateaus out. You can see that on the yellow and the blue, on the red, and then around about this position here, the say 45 milliseconds, the contacts are more or less at their maximum separation. And what you shouldn't see is what we're seeing here, and you can see there's suddenly a large increase in the vibration, and probably what's happened there is that the damping is starting to become slightly less effective, so it's actually now creating another vibration within the circuit breaker, and that obviously needs to be resolved, otherwise it'll sort of shake itself to bits. Okay, so I think that's me finished, so back to you, Martin, if we want to take some questions.
Indeed. Thank you, Phil, for a very informative presentation. I have two on the screen at the moment. The first one is if a GIS circuit breaker 132 kV is not tested to perform reactive switching, we intend to install an additional AIS circuit breaker in series with reactive switching capability. I presume in this case, the GIS circuit breaker will still be subject to reactive switching. Is there any solution to counter this situation, please?
I think I have to go away and think about that. I mean, I'm very good at telling you defects in circuit breakers. I wouldn't say I'm particularly an expert in circuit breaker applications. If you could send that to me, Martin, I'd prefer to think about that and send an answer on.
I will do.
Yeah.
No problem at all. Another question. Did you identify the root cause for this capacitor failure? For example, was it in manufacturing process? I think that was a grading.
The grading capacitor, I think the answer to that was probably no. I think the investigation was done to try and satisfy the utility that in fact they'd done the right thing. So, we'd gone along and we'd said, oh, you've got this problem with the grading capacitor, and they said, okay, right, well, let's see if you're right. So they were, proving it, and then obviously it was shown to be the case. You'd probably be better off speaking to somebody from the utility about how they would deal with that situation. I don't really know whether they're probably just glad that they'd found something and they could, put a new one on and move on from it. Exactly how they look at it in detail.
Another question, for switching reactor current, the lower the current, the more onerous the switching duty is for the circuit breaker. Can it be explained, please? Do you want me to give you that again?
Yeah, I'm just trying to think of the answer there. So I think this comes to the fact that in some SF6 interrupters, if you don't have a large arc, it actually reduces the amount of gas that goes through the arc to cool it down. So particularly in a shunt reactor, you don't have, in the shunt reactor, peak current's only about 280 amps or so. It's not really very large. So you're not producing a very large amount of gas, large amount of heat when the arc is burning. It tends to, some of these breakers throttle back. They have little valves in them that stops the full gas flow. And what that does is that when the arc goes out, it completely sweeps away any of the arc products, which means that if the breaker then goes on to reignite, it reignites dielectrically, which means you get this effect that I showed you with the puncturing the holes in the nozzle. Now, if the arc was very, very large, the gas flow is not quite as good at getting rid of all the arc products. So when it reignites, it can do it quite gracefully with what's called a thermal reignition. So I think maybe that's what's the issue there. If I have any more thoughts about that, I'll happily answer that one on email as well.
We have a question from Marcel, a very regular attendee of our monthly technical webinars from Switzerland. Excellent introduction. Thank you, Phil. Question, not being an expert, is this monitoring widely applied worldwide, or at least in the UK? And what are typical indicators on when and where to place the monitoring equipment? Should one go through all the equipment to have a status estimation on equipment health?
At the moment, we've only trialled this with National Grid. I wouldn't say we particularly have a great commercial offering on this. It's more of a service offering. I think, and again, I'm not sure I want to speak for National Grid, but I would say that what they would like to do is to apply this to as many breakers as possible to sort of get a benchmark. So, although I've talked about shunt reactors, we've used it on other types of circuit breaker, and it has produced, very good results in other applications. And I think they quite like the idea of if, for example, if you're going to go in and do maintenance on a breaker, you might get us in to sort of see if there's anything wrong with it before you start the maintenance, to make sure that if we go back afterwards that they've not introduced any new defects into it. I mean, in my personal view, I would say you should be putting this on all the shunt reactors. I mean, I think most line breakers might only operate once a year, and that's on the yearly test, whereas a shunt reactor or a cat bank, something like that, they're operating every day. They see a very, very high duty, and as I've demonstrated from this presentation, there are hidden defects in there which this equipment is able to reveal.
Good news. The question for Gaurav that you said you would take away and look at, Matthew Isles, who's our regular member for A3 in the UK, has provided some guidance on that. So that's...
thanks, Matt. I was almost just about asking whether you could answer that for me. Thank you.
There is a question. Has this type of unit, this type of equipment, been type registered for National Grid?
Again, Matt might want to chip in on this one as well, but I think you only type register in-service equipment. This is only monitoring equipment, so okay. You wouldn't. I mean, they've sort of de facto approved it in as much as we're using it.
Okay, there's a question there from Minoru that I can't quite. Do E-field and RF sensors affect for GIS? How PD detects GIS? Don't quite understand that.
Sorry, just read it again.
Do E-field and RF sensors affect for GIS? Or are they used for GIS?
Okay, so I can just say a couple of words about that. So in an AIS, we would use the monopole sensor that I showed you with the G clamps onto the frame. In a GIS, we would use the internal PD sensor, and depending upon the manufacturer, most internal PD sensors do produce a little bit of 50 hertz. So we're able to simultaneously take the 50 hertz and the RF from it. I don't think there's any much more I can add to that, to be honest.
Okay. One last question. You mentioned capacitor banks. Is there a similar issue, and is this worth monitoring too?
Yes and no. I mean, the thing about when you open a capacitor bank is that if you think about I made the point that the system, when the arc goes out, the system voltage remains more or less the same, whereas the reactor terminal voltage very quickly goes somewhere else. In a capacitor bank, you don't get that. In a perfect capacitor, it would the voltage would remain exactly the same. They usually have reactors to try and discharge them slowly. But as the arc goes out, there's not a very large difference in voltage across the contact, so you don't have the same issues. But that said, they do operate every day, so it's useful to be able to trend things. You certainly know all the metrics to do with the arc instability signals. They're very, very relevant to any breaker as well. So we certainly have used it on shunt mechanically switched capacitors. It's just that we've never found any problems. People like to see gory photographs, don't they, of things that have gone wrong?
Yeah. Phil, thank you very much for taking the time and effort to make your presentation today. Certainly appreciated by many people attending the webinar today. And for everyone that joined, again, thank you for joining. I hope you got some value out of this. I certainly did. And I look forward to talking to you again next month. I don't think we've released the details for the October technical webinar. That's about to come out very soon. And again, Phil, thank you very much.
Thank you, everybody. Have a good day.